and we are here to continue talking about waves, right? And today we will talk about the interference of wave, and this is where, because of the interference of wave, we are going to have two types of interference that we will study in detail: the double slit experiment and also the standing waves. Okay, so where's my full screen? Hang on. Okay, so let's talk about the superposition principle first. Okay, last class on Monday we have spent a lot of time deriving the wave equation, and it involves a lot of math. But don't worry, I told you on Monday, right? Even though there's a lot of math, hang on, it's too bright. Even though there's a lot of math, it's not so important because this is the math that is outside the course. What I want to use for us today is the wave equation itself. Okay, so this is the equation that I want to use. Okay, so I want to use up to this point. Okay, so the wave equation is satisfied by this, right? And if you remember, any function that is having the property of kx minus omega t is the solution to the wave equation. What does it mean by a function that is a solution? That means if I differentiate this thing and differentiate this thing, then it is related to this equation. So the left hand side is going to be equal to the right hand side. If it's not a solution, right, if I differentiate, I put it here and it's not the same as what I got here. If it's not the same, then it is not the solution to the wave equation. So that is we have derived this for a general f, and then we will, and also I was briefly mentioning a particular solution that for the special case. So this is reviewed last week, right? So a special case, it is what we call a sinusoidal wave. Right, so a sinusoidal wave is ytx is equals to some amplitude and then a sine. Actually, cosine also can, right? It will satisfy the same equation. Okay, so you find that this is equals to kx minus omega t, right? And if I differentiate this y twice with respect to time, so if I differentiate this with respect to time twice, it's going to give you negative omega square, and then it's back to sine kx minus omega t, right? And if I differentiate x twice, then I'm going to get negative k squared, and then I got a sine kx minus omega t. So therefore, right, so therefore if I divide the two, partial y partial t square divided by partial y partial x square, right, what's going to happen on the left hand side? So in the Monday class, I have derived it for the arbitrary function y as some function, but for here my function is a sine this thing. So let's see what happens. I got a sine kx minus omega t, and then divided by minus k square a sine kx minus omega t, right? And then we cancel these two terms, actually can cancel. The minus minus also will cancel, and I got omega square over k square. So if I bring this term to this side, I got partial y partial t square is equals to omega square over k square, and then I got partial y partial x square. So this is satisfies the wave equation, right? So this is the same equation as this if omega over k is v. So this satisfies the wave equation if v is equal to omega over k. Okay, so this is our condition over here. V square is equal to omega square over k square. So in general, because you can have plus and minus, that will tell you the direction of propagation. But in any case, we have the wave equation and we have a solution to the wave equation, right? So this is how we check that something is a solution, right? So this is a quick review of what we did on Monday. So now what we are going to do now is to talk about the superposition principle. So the superposition principle is actually a theorem from math about differential equations. So I will, again, you will learn more detail in math, but I will show you how this works, because superposition principle is important in many areas of physics, especially electromagnetism and quantum mechanics later on. So they rely on the superposition principle. And interestingly, right, gravity does not have superposition principle. So that is the differences there. Okay, so what does the theorem says? So let's say, right, if I have two solutions, so f1 and f2 are solutions to the wave equation, Okay, so if I have two solutions to the wave equation, then I can create a new function which is the sum of f1 plus f2, and it is also a solution. Okay, so solution to the wave equation, what does it mean, right? So solution to the wave equation, so what does it mean? So let me write this here. This means, okay, so if f1 is a solution, right, that means if I differentiate f1 twice with respect to time, it is going to be equals to v square differentiating f1 twice with respect to position. Okay, and f2 is also a solution, so that means if I differentiate f2 also, I get the same thing but for f2, right? So this is v square partial square f2 partial x square, right? So I got this equation is satisfied, this equation is satisfied. That means if I differentiate f1 twice with respect to t, it is going to be equals to this combination. If I differentiate f2 with respect to t, it is going to be equals to this combination. And now what I'm going to say is f1 plus f2 is also a solution, right? The big F. So yeah, so let us easily show this by direct calculation. Let's say, right, on the left hand side, what happens if I differentiate the big F twice with respect to t? So f is f1, f2, so that means I'm differentiating twice of f1 plus f2. Okay, so differentiating a function plus another function is just the sum of the differentials, right? So I got this is f1, and then partial this f2, and then this with respect to t. Okay, and then according to my equation 1, this thing, right, so this thing is equals to v square d2f1 dx square, and this thing is f2, so this thing is actually f2, right? So this thing is actually v square df2 dx square, right? So this is because of equation 1, and this is because of equation 2. Okay, so this is equals to this, and then I can actually take this out because this is the same as v square second derivative and then f1 plus f2, right? So it's just the same. This line is equals to this line because you can expand to get this back, and f1 plus f2 is the big F, so this is v square partial square f partial x square. So this big F also will satisfy the wave equation, right? So that is the proof of my superposition principle. Okay, so this is what we call the superposition principle. Okay, so what does it mean by having a superposition principle? The physical meaning, right? So this is the math, right? But physically, what does it mean by having f1 plus f2? That means the two waves can be on the same system at the same time. So that is what it means. Okay, and then you can just solve it in the usual way. So let's take an example, right? So let's say with, for example, superposition of waves on a string, right? And we were learning about a string last time, right? So so let's say I have one wave that is propagating to the right, okay? And then I have another wave that is propagating to the left. Okay, so I'm going to call this wave 1 and then wave 2. Okay, so a wave is any shape of a graph that is moving in one direction. Okay, and I can go to the left and right, right? I've shown you all the examples in on the Monday class. So let's say I have one wave coming here and one wave coming here. So I'm going to call this F1, I'm going to call this F2. So these two are the solution at all times. So they're going to combine, and so the vertical axis is just this is y is equal to f1, and this is y is equal to f2. So it's like f1 plus f2, like literally on the string. So if these two string, right, they're going to combine together. So they're going to come and meet together, right? So when they meet together, they just cancel each other out, right? So yeah, so they just like cancel each other out like this. And then after they cancel each other out, they actually continue moving, passing through each other like this. Right, so you got wave 1, wave 2 has come to here now, and then this was wave 1. I hope you understand what this means. This is the string, right? So this, and then becomes this. Okay. Correct. So yeah, so if you take sound as the wave, right, it can actually happen like this. Okay, so that is actually why, right, if you watch a musical before, if you attend a theater musical, right, they actually design the musical hall in a very special way so that your sound is reflected in a way that doesn't cancel each other out. And then also, speaking of cancelling sound, you can also buy the noise cancelling headphones. So in some way, they make the sound wave cancel each other so that you are not disturbed by the outside noise. But around has music. You mean in the musical hall, right? Yeah. So it's very complicated. I don't know how they works, but somehow they design. And also about the reflection also, the design is also important about the reflection, the echo, right? So because normally inside a big room, when you make a sound, right, you will hear the echo. So if you perform music with echo, it doesn't sound nice. So you need to design your sound stage such that the echo does not cancel each other or somehow. I also don't know how it works. Surround sound, that one also I don't know. Surround sound, I think surround sound is how they not really. I don't think so, because the surround sound should work in any room in any person's house, right? So it's just the illusion of how they lag the sound from two speakers so that they create a 3D effect. How can make the kind of headphone? I don't know. Is it probably depends on material. So this one, this one I'm not sure. But about the surround sound, right? Yeah, that one is another interesting thing, because how do you make surround sound depends on how do humans can detect sound from different directions. So have you wondered, right? When you hear a sound, right, you know what direction the sound come from, right? And why is that so? It's because, right, the main reason is you have two ears. Fourier transform, not really, not specifically for this. Doesn't have Fourier transform is coming in for sound analysis but not in this part yet. Not about the surround sound. So for the surround sound, right, how do we know if I hear a sound from my right side? How do I know the sound come from there? It's because we got two ears. And not Doppler effect yet. We actually learn Doppler effect later. And the reason is because our right ear actually hear the sound first before the left ear, right? So there is a time delay, right? So that is from there, our brain can somehow calculate the direction where the sound is coming from. So that is the reason why we hear sound coming from different direction. So if you want to create a surround sound, right, usually you need two speakers or you need two headphones. And then even when you for games or things like that, right, if you want to make the effect that the sound is coming from one direction, you make the left speaker make the sound slightly earlier than the right. So there's a slight time lag, and then when you hear on the speaker, you feel that it comes from this direction. Okay, so that is the reason. So that is an interesting piece of way to design sound design. Okay, so let me mention this a little bit more about this. So this sound is like they cancel, the two waves cancel each other, right? So this is because one is up, the other is down. So this is later we will know this as destructive interference. So if the two waves are in the same, right, the same orientation, right? So I got wave 1 and wave 2. Okay, so F1 and then F2. So when they come to each other, it will be even greater, right? So this one is F1 plus F2, right? So over here they cancel each other is because F1 plus F2 is equals to 0, right? So F1 and F2 is even larger. Okay, and yeah, so it depends on your function, and I don't care what my function. I'm just drawing pictures. So they will combine and make it larger, but they continue to pass through each other. So the wave 2 will continue to pass through here, the wave 1 will continue to pass through here. Okay, so this is what happens when two waves are passing through each other. Okay, so that is the that is the general description. Okay. Yeah, no energy loss. Yeah, it's not cancelled. It's not totally gone because it's only instantaneously at 0, but it will continue to pass through each other. Yeah. So it's because that's the superposition principle. The energy is still there. It's just that at one instant it has 0 at this moment, right? But there's instantaneous velocity and instantaneous acceleration. All still present into the system. Okay, and that is the physical consequence of why superposition principle is true, right? So it doesn't matter F1 and F2, right? So F1 is a solution by itself, F2 is a solution by itself. They don't really care about each other. You can add them numerically and you get the addition results, but after everything finished, they continue by themselves, ignoring what happened just now. Right, so that is the idea of the superposition principle. Okay, so it works for sound wave, it works for water wave, it works for waves on the string and things like that. There will be two solutions. We are about to consider this case. Yeah. Yeah, so another way of saying, stick together, as in if they don't get stuck at 0, right? Then if you let them continue moving, then they will continue to pass through each other. So under what condition we have two distinct solutions, right? Is very common, like the two water waves, right? If you, like in the water, right? If you drop one stone here and then you drop another stone here, then the two waves will approach each other and then they will cancel or add up to each other. If you shine two light sources on the same region, then the two light will affect each other as well. Okay, so that is the two physical situations I can think of. Sound, like the speaker thing, right? The noise cancelling headphones, something like that. That will also happen as well. So but let us see what happens to our function, right? What if I interfere two sinusoidal functions together? So what I'm going to do is we are going to combine two waves of different phase. Okay, so I'm going to combine two waves of different phase, and let's say I have one wave, so I'm going to just call this y1 tx, right? And then it's equals to some amplitude and then sine. Okay, and I have kx minus omega t. So this is one wave, and then I have a second wave that is a different phase from the wave 1. So remember what was phase. This is the phase. Whatever is inside the sine function is the phase of my wave. So this is the phase of y1. And then my y2 is, let us assume they have the same amplitude, and then the phase is different. So if I write kx minus omega t, then these two phases are exactly the same. But if I have an extra term, right, something, okay, so it's a constant, it's some number, right? So if this number is not 0, then these two phases are different. So this is the phase of my wave 2. Okay, so that is the phase, right? And this is why if you read the textbook, right, people talk about phase difference all the time. Phase difference. So what is the phase difference? Phase difference between y1 and y2 is equals to, well, this phase minus this phase, right? So let me take phase of y2 minus phase of y1. Okay, and then so you realize that it's just phi, right? Omega t plus phi, and then minus kx minus omega t. So the kx cancel, the omega t cancel, and the phase difference is phi. Okay, so this is the phase difference between the two waves. Okay, so if I draw on the picture, right? So let's say if I draw on the picture, and remember the wave has two variables, so it's it depends on time. So I need to draw if I have to draw something, I have to draw it on a fixed time, right? So let's say I have so let's say this is my wave 1, right? And then I have this phase that is plus by some number. So if I plus by some number, usually what you do is it has to move back by a bit, right? Yeah. Okay, so that's why you see that there's a difference between the two. Okay, so that is the idea of the phase difference. Okay, so we will learn how to calculate the different situations in the different cases later on. Okay, so let us consider the interference of these two waves. Okay, so now we can because this is just plus a constant, right? You can easily show that y2 is a solution for the wave equation. y1 is a solution of the wave equation. So these two are solutions. So by superposition principle, right? Since y1 and y2 are solutions to the wave equation, then by the superposition principle, I can create a new function which is just y1 plus y2 is also a solution. Okay, so does everyone follow so far? Okay, so wave on water. Yeah, so everything is the same thing, right? The water wave, guitar string, sound wave, they pass through, but after it pass through, it will continue moving on. Yeah. So yeah, so y1 plus y2 is also a solution, and I'm going to, so on Monday I told you don't worry about math, but today's math is a bit important, so we have to follow what is going on here. So for y1, right, my y1 function is sine kx minus omega t, and then my y2 is sine kx minus omega t plus the phase difference. Okay, so how do I add up these two numbers? Okay, so how do I add up these two numbers? I'm going to use the formula, the trigonometric formula. So sine theta plus sine phi. So the y0 I can take out as a factorization. So let me factorize y0 out. Okay, so what is sine of sine plus sine? So sine plus sine, right, there is a trigo formula. So sine plus sine is 2 sine of theta plus phi over 2, and then cos of the difference, theta minus phi over 2. Okay, so this is a formula that you probably learn in the high school, or in Wikipedia you can also get it, right? So sine of something plus sine of something is 2 sine cos, right? So how do we work this out? Well, this is equals to 2, then there's an amplitude here, and then there's a sine this plus this over 2. So that means this thing plus this thing over 2. So kx omega t twice. So 2 kx minus 2 omega t plus phi 0 over 2, right? And then cosine of this minus this. So this minus this, they cancel each other out. So this minus this cancel each other out. I got negative phi 0 over 2. Okay, and cosine of negative is the same as cosine of positive. So let me put it here. Cosine is an even function, so it's cosine phi over 2. And then this part is just sine of kx minus omega t plus phi over 2. Okay, so this is my solution to the wave equation, having two waves at different phase adding up together. Okay, so this, notice that, right, this part is a constant, right? So this part is a constant. So this, and then this part is sine of, this is a sinusoidal wave part. So the conclusion is the result of interference y1 and y2 is a new sinusoidal wave and then new amplitude is equals to this whole thing. So 2y0 cos phi 0 over 2, right? And notice that my amplitude, this one is depends on the initial amplitude, is still there, but then there's a cosine of this. So the amplitude depends on the phase difference. Okay, so that is my new amplitude. Oh, yeah, I guess in the form like sign this, give the answer. I mean, if you want to calculate, if you keep it like this, right, then we don't notice the new wave is this is the amplitude, right? So unfortunately, we have to use the formula to recognize that my result of the interference is actually just another sinusoidal wave, and another sinusoidal wave where the amplitude is given by this formula, right? So unfortunately, yeah, this is where math is important to help us derive a new physical result, right? So sometimes we cannot avoid that. Okay, so yeah, so let us calculate this quantity over here, right? So again, right, let me draw the two situations. Let's say I have this thing here, right? So my the argument of whatever, so remember the phase is the argument of the cosine, so I can plot this as a phase, and phase is measured in radians, right? And then this is my vertical, so y. Okay, then let me try to draw a nice picture. So let's say at time 0, then kx is equals to the phase, right? So time is equals to 0. So when time is equals to 0, right? When time is equals to 0, the phase is just kx. So the horizontal axis is equals to k times x, right? And then my graph is a sine graph, so like this, like this, like this, and then it continues going on, right? So after one cycle, the phase is 2 pi. Half a cycle, the phase is pi, right? So this is pi over 2. This is 3 pi over 2. So everyone knows how to draw this type of picture, right? If not, you should get familiar with it because it is quite important to determine the situation like this. Okay, so then so let's say the blue one is for wave 1, and then let me draw another picture for wave 2. So just everything move to the left by a bit. Right? And then you see that it's the same graph, but it's moved a little bit by some lag, right? So this is the phase difference. Okay, so this is the phi 0, right? So that is the difference between the two waves. So if the phase difference is 0, if there's no difference, then the two graphs overlap each other exactly, right? And then if my phase difference is actually 2 pi, if my phase difference is actually 2 pi, right, then the graph is actually overlap to the next stage. So it's the same picture overlapping again, and then and so on and so forth. So you can from the different values of phase difference, right, you can actually draw the difference of the two graphs properly. Okay, so this is where we have the different situations for constructive and so this is a general interference principle. Then now let us consider two special cases, the constructive interference and destructive interference. So by now I guess you can see what is going on already, especially if you're already familiar with the phenomena. Over here I just come from the direction of trigonometric functions, right? So what happens for constructive interference? Okay, so for constructive interference, right, it happens when your phase difference is equals to integer number times the cycle, so it's 2n pi, right? So n can be 0, 1, 2, 3, or negative numbers, right? Then another way of saying is the two waves are in phase. Okay, so then if I interfere these two waves, right? So basically the wave 1 is the same, the wave 2 is the same, right? Okay, so wave 1 is the same, wave 2 is the same, and then what happens to my graph? So my wave, the superposed wave is given by this formula, and let me write out this formula here. So y is equals to 2 amplitude cos, and then my phi is 2n pi, and then my sinusoidal wave is kx minus omega t, right? So this is y1 plus y2, right? But what is so what is cosine of integer n pi? Cosine of integer n pi, right, is just either positive 1 or negative 1, right? So the amplitude of this is 2y0 sine kx minus omega t. So the interference, right, so the interference of these two waves, right, it will give you a new wave that the amplitude is twice as big. Sorry, it's off screen. Yeah. Okay, so if I interfere these two waves, I get a wave that is twice as big. Okay, so by the same logic, right, let us see what happens for the destructive interference. So destructive interference. Okay, so the destructive interference is the phi 0 is some integer times pi. So n can be well 1, 2, 3, not 0. Okay, and we say that the two waves are out of phase. Okay, or we can say that it's a half cycle out of phase. Okay, because, right, what happens, y1 plus y2, right, is going to be, according to my formula, is over here, right? So I got 2y0 cos, and then integer pi, so this term becomes integer pi over 2, right? And then I got sine, and then I got sine kx minus omega t plus phi 0. Hang on, it should be odd integer, right? So it must be 3, 5, odd integer, right? So cosine of odd integer pi over 2 is what happens, it becomes 0, right? So this is equal to 0 if n is odd. Okay, so that means then this whole thing will become 0, right? So that is the destructive interference. So in the picture, right, how does it look like? So the wave 1, okay, so the wave 1 is like this, so 2 pi, right? Then my wave 2 is shifted by an odd number of integers. So let's say I got this, something like this. Okay, so it's always opposite to the wave 1, right? So wave 1, right? So as you can see, right, this is positive y0, then this is negative y0. So positive y0, negative y0, if I add up, then they become 0, right? So same is true for all the other points. So these two are opposite to each other. So if I interfere, right, if I interfere, I just get flat, nothing, right? So this is flat, right? So the new wave becomes 0. So this is how we get destructive interference. Okay. Yeah, so any questions so far? Okay. What time is it now? Okay, so if there's no question, then I guess everyone understands the concept of interference things, right? It's something that people have learned in the high school before, but for us is like, where does it come from, right? We actually solve this from the wave equation using the superposition principle, and then taking two sinusoidal waves, we combine the two sinusoidal waves using trigo functions, we got this, right? So this part is the amplitude, right? And then the amplitude depends on the phase difference. So if I choose the phase difference correctly, I can get the largest possible amplitude I can, which is twice of my original amplitude, or the total amplitude becomes 0, right? They cancel each other out, right? So we can derive the condition where they have interfere constructively or destructively. It can only happen at some original points. Throughout the whole line, yeah, so how to get YTX? Which YTX? It's just a sinusoidal wave, right? It's nothing to get. It's the solution I continue from Monday. So for this picture I draw is through the whole line. That is when the two waves are passing through in the same direction. Then it's always 0 through the whole line. Then it's totally flat. But what I'm going to do next is to consider the two waves coming in the opposite direction. Then it's only 0 at certain points. We shall see later. Okay, so yeah, so YTX is just sine kx minus omega t, so there's nothing special there. Okay, so it's just a sinusoidal function. Okay, so yeah, to answer the question of the waves coming in two different directions is actually the topic of standing waves. So standing waves. Okay, so standing waves, right, is happening, yeah, most definitely in the things that we discuss so much is about it happens for the guitar string. So let's say I have the guitar, right, the top of the guitar and the bottom of the guitar, and then if I don't touch the string, it's just going to stay there, not moving over here. But then if I plug the guitar, the string will start to vibrate, right? So it starts to vibrate something like this, and let's say the total length of the string is L. Okay, so the total length of the string is L, and then and another thing to take note, right, because the guitar string is tied to the top and bottom, is tied down, so it cannot move. So this is the endpoints of a guitar string is fixed. So in this situation I have a string with fixed endpoints. Right, so that means, right, if I'm talking about the solution YTX, then my YT at x equals to 0 is always 0. My YT at x equals to L is also 0. So let's take this to be my x-axis. So at this point is x equals to L. At this point is my origin, x equals to 0. Okay, so then the vertical direction is my y. And then if you remember from last week, we have discussed this, we have derived the velocity of the wave is the tension divided by the mass per length of the string. Right, so this is the speed of the wave. Oh, you want to talk about string theory? Okay, yeah, why not? Then we can talk about the 11 dimensions, 10, 11, and 26 dimensions, and all this kind of thing, right? So string theory is basically kind of similar to this. That's why it's called string theory. They are talking about the vibrational modes of this thing. So we're going to talk about that. So in a way, in some sense, this is already string theory, right? Just that for the string theory, right, each string represents a particle. But right now, our string is actually a real string, right? A guitar string. So let us try to solve this situation. Okay. So now, what is the most general not the most general, but what is the non-trivial situation that you have on a string? So if I plug a guitar string, right, the wave can travel to the left, or maybe I can make a wave travel to the right. Okay, so if I travel to the left, right, for a string with fixed endpoint, when I come to here, this is fixed. So what will happen to the string? If the wave travel to the right, what's going to happen is it's going to get reflected because it's tied down. So there's nowhere to go further to the left. So when the traveling wave comes here, right, it will get reflected and go this way. Okay, then if I come here, right, and then I go to the right boundary, so at the right endpoint, it's tied down. This is fixed. So this string cannot go any further. So what the wave can do is it will get reflected again. So what's going to happen is you just have the two waves reflecting left and right onto each other. So the simplest situation that I will consider is let us calculate now to have one wave traveling to the left and another wave traveling to the right. Okay, so that is the simplest situation. Okay, so let us consider a wave traveling right. So I'm going to call this y1 and another wave going to the left. Okay, so I'm going to call this y2, right? So y1, right, is a function of tx is equals to a sinusoidal wave kx minus omega t, right, is traveling to the left, assuming k and omega are positive numbers. And then y2 is, right, if this k and omega are positive numbers, then if I have a minus sign, that means the wave is traveling to the right, right? I drawn all the pictures on Monday, if you remember. Then for the wave traveling to the left, let us assume no phase difference, but it is going to the opposite direction, so I plus omega t, right? So this wave is traveling to the right, and this wave is traveling to the left, right? So traveling to the left, right? So when they interfere to each other, what's going to happen? So I'm going to use our trigo function again. Let us add up the two functions. Okay, so y1 plus y2 is equals to this plus this. So I got, well, the constants a I can factorize, right? And I got sine kx minus omega t, and then plus sine kx minus omega t. Okay, and I will use my trigo formula. My trigo formula says that the answer is, well, there's a 2 here and then sine and cos. So the sine is the sum of these two divided by 2. So this plus this divide 2. Hang on, plus. Okay, so kx minus omega t plus this thing. So kx plus omega t divide 2. And then I got cosine of the difference. So this minus this. So kx minus omega t minus kx minus omega t divide by 2. Okay, so we can simplify. Omega t cancel. This becomes 2kx divided by 2. So I just have a sine of kx. And then this is a cosine. So this time the kx cancel each other, then I get negative omega t, right? 2 omega t over 2. But cosine of negative is the same as making it positive. So what I have now is 2a cos omega t sine kx. Okay, so this is my new solution of my wave equation. Phi over 2 in the sine. Is it? Wait, let's check. You mean here? Oh, yeah, you're right. Oh, yeah, you mean here, right? Plus phi over 2. Yeah, thanks. Amplitude plus phi over 2. Yeah, I forgot the phi over 2. So I forgot the other one as well. No, this one got. Correct, right? Yeah, this one got. well, we shall assume no energy loss. Yeah, ideal case, so no energy loss. Okay, so this is the equation representing a string, the wave moving left and right into the string, right? So it pass through each other, and then later it's going to get reflected again, so it's going to pass through each other again. So generally speaking, is at the end is always this situation. So in your year 3, right, so this is where Fourier transform starts to come in. I'm only solving two waves passing inside the string. And the most general case is actually there's infinite number of possible waves passing through the string, and we can only solve this using Fourier series and Fourier transform. Okay, so maybe that's what reminded, was it Yiming who mentioned Fourier transform, right? So that is where that will happen. This is only one term of a Fourier series. So that is and one way of saying our solution here. Okay, so so since we got this solution now, but what is our k, what is our omega? Actually, right, it depends on our endpoints. Remember that my function is a string with fixed endpoints. That means when position is 0, this function must be 0. So let's check the endpoints. Okay, so the first condition is when yt0, that means if I put in x equals to 0, so 2a cos omega t, and then this thing, the whole thing 0 equals to 0, done, right? But my second endpoint, lights. My second endpoint is when x equals to L. So let's see what happens when x equals to L, right? So this is where the interesting thing happens. So this is 2a cos, well, omega, any t, right, don't care. But what happens when x is equal to L? I got sine kl, but according to my fixed endpoint, right, this must be 0, okay? So must be 0. Okay, so how can I make this equation to be equals to 0, right? So to satisfy this endpoint, ytl. So if I want to make this equation equals to 0, well, how can I do that? Well, a cannot be 0. If a is 0, then there's zero solution. Omega t is a function of time. So as time changes, this will always change. So I cannot guarantee this to be 0 all the time. So the only possible way is to make sine kl equals to 0. So the only possibility is sine k times l is equals to 0. Okay. So when is sine kl equals to 0? So sine kl is equals to 0 when kl is equals to an integer number times pi, right? So n is an integer. So n is 1, 2, 3, ... So that actually that gives us a formula for k. So k is equals to n pi over l. Okay. So so now we got a condition, a constraint or condition for k. And remember what is k? K is the wave number. Okay, so k is the wave number. And remember what is the definition of the wave number, right? So our sinusoidal wave, right? For sinusoidal wave, yeah, so just now Charles was asking where to get ytx. Is not where to get, it is a sinusoidal wave. That means ytx is sine kx minus omega t, right? And then my wave number is k is 2 pi over lambda, right? And then my omega is 2 pi f, right? So remember all these definitions. The a is the amplitude, this is the wave number, this is the wavelength, this is the angular frequency, so this is the frequency of the wave, right? So that means I got the condition for the wave number. That means is 2 pi over lambda is equals to n pi over l. Okay, so if I cancel the pi, I can actually get a formula for n. So a formula for lambda in terms of 2L over n. So this lambda can be different wavelengths for different n. So the wavelength of this solution, right, it cannot be any wavelength. It must satisfy this formula for integer n. So n equals to 1, 2, 3, dot, dot, dot. Okay, so this is the first time we see this kind of quantization condition. You will encounter a similar situation in quantum mechanics, and the reason why in quantum mechanics that the energy can be quantized, discrete number, right, is similar calculation to this. So here we got the formula for the wavelength. The wavelength of a string with fixed endpoint cannot be any continuous value. It's only fixed by this formula. Okay, so only has some integer number of possibilities. Okay, so yeah, so let me draw the situation just to see what is going on. So let's take, for example, right, for the case of n is equals to 1. So when n is equals to 1, right, then my lambda is equals, my wavelength is twice of L. So what does it look like? That means if I have a string, right, so I have a string from 0 to L, then my wavelength is twice of the length of my guitar string. So that means my wavelength is actually like this, and then like this. But this part is not the string, so it's only half. The guitar string can carry half the wavelength, right? And what if n is equals to 2? So if I put in n equals to 2, right, 2 and 2 cancel, so the wavelength is exactly equals to L. So what happens on my guitar string is this is my L, so this is half of the L, so the wavelength is one wavelength is exactly fitting inside the length of the string, right? And what happens for n equals to 3? So for n equals to 3, 2/3 L, so 2/3 L. Then if I draw the picture, so L is here, so 2/3 is going to be, let's say 1/3, 2/3, 3/3. So it's going to be like this. Okay, so again, right, I'm drawing this picture for t0, t0, t0. So as time goes on, right, it's going to change the shape. N is the number of cycles. Do you call this the number of cycle? Yeah, right. So n is not really the number of cycles. It's just like the number of wavelengths that you can fit. Is just this picture lah. Is this picture? I don't know what's the word to use for n. N is the technical term is n is the mode. Is called mode. Okay, so for different n, right, you can fit the different guitar strings into it over here. Okay. Wow, it's already 3:54. So, what should we do? Hang on. Okay, so should we break now or? Yeah, if you guys don't mind, right, let us finish because we are almost finishing this topic. We just need to calculate the frequency. Okay, so let us finish this off and calculate the frequency related to this. So it's just a bit more calculations. What is the frequency for each n? Okay, so n equals to 1, 2, 3, 4, right? This is where we get the harmonics on the guitar string, right? So our formula for lambda is given by this, right? And then the frequency, right? So how do we get the frequency? Let us remember that the formula for velocity of string is given by omega over k. And then on the Monday's calculation, for a string of tension F0 and mass per length mu, then my velocity is equals to the square root of F0 over mu. Am I right? Okay, so let us simplify this on the right hand side. Omega is 2 pi over lambda. Omega is 2 pi f, the k is 2 pi over lambda. Right, so I got the situation where F0 over mu is equals to cancelling. This is equals to F times lambda, right? And what is my lambda now? So the lambda we have derived the lambda to be 2L over n. So this is the frequency times 2L over n. Okay, so we can actually calculate the frequency formula now. It is just n over 2L. If I bring this over, it's equals to F0 over mu. Okay, so the frequency of the vibrating string actually depends on the on all these quantities. Right, so that's why when we were talking about the guitar string, right, the guitar string depends on the tension, it depends on the mass per length, right? So these two are, if you don't touch the guitar, it will be fixed. The length is fixed, but it also depends on the n as well, right? So the length of the string you can actually change it by changing the guitar part, right? So I still have my guitar here, okay, and as guitar players will know, right, the frequency of when you plug the guitar string, you will hear the most of the sound comes from the fundamental frequency, right? And then if the tension depends on the tuning of the guitar, so that's why you got the tuning over here. So if you adjust the tuning, you're actually tightening or loosening the string. You're changing the tension on the string. The mass per length is the material, right? How the string of the guitar, this is like some piece of metal, the top part is brass, so it has a certain, depends on the material of the object, it has mass per length, which you can calculate and you can measure. You just weigh and measure divide by the length, right? And then you can change the frequency of the string. That's why people press on the fret, because if I don't press anything, then you get the full length of the guitar. But if I press down on the string somewhere, you are shortening the string. So my original sound, right, is like this sound. So if I press down on the string, I shorten the length of the string. So if I shorten the length of the string, the frequency will be higher like this, right? So it's higher than the original sound. Okay, and then all this, the harmonics also come in when you play harmonics on the string. So if the open string, you just get the fundamental mode. But if I do the trick to play the harmonics, right, I put my finger near, let's say, my halfway point of the length of the string, so it's about here, the 12th fret. Then I get can you hear the sound of the first harmonic? Then the third harmonic is the 5th fret, I think. 7th fret. Yeah, something like that. If it's not clear, I don't know if the microphone is picking up, but that's about it. Okay, so yeah, time is dragging too much, so let us go for the break, and we shall continue with tutorial after this. Okay, so yeah. Test. Okay, so now let's do some tutorial questions from tutorial 8. Okay, so let me say tutorial 8 here. Okay, so let's start with some basic stuff. Question 1, right, in case we all forget stuff from tutorial. So let me take out the ocular. Okay, so this is our tutorial 8. So let us start with question 1, right? Let us read the question first. So I have an object undergoing simple harmonic motion with this period given and then amplitude given. At time 0, the object is x equals to 0, moving in the negative x direction. So from there, I want to calculate the position at this moment later. So how do we solve this type of question? We just need to use the general formula for oscillating simple harmonic motion. Okay, full screen. Okay, so the info given to you is the period given 1.2 seconds. The angular frequency can be calculated from the period. So if we put this in, we get 5.236 radians per second. And then the amplitude also given 0.6 meters. Okay, so the general expression for, wait, let me check what you guys are saying. Yeah, so we are a PHY course technically, right? And in my case, really see what the office tells us, confirm with us. Yes, I'm still waiting to hear from the office about our camera. For the math, maybe yes, but for us, I don't know yet. Yeah. So anyway, we have the amplitude already. Our general expression for our oscillating wave, if you remember, is always for here is cosine omega t plus phi 0, right? And phi 0 is our initial phase of the system. And then later we are also going to need the velocity. So the derivative of x with respect to t gives our velocity as a function of time. So differentiating this gives me a negative omega a sine omega t plus phi 0. Okay, so the information given to us is at time 0, the position of our object is at 0. So that means if I put t0 here, this is equal to a cos 0 plus omega t. Okay, so how can I make this equal to 0? So that means my phi 0 is either a half integer, right? So n is an integer. Okay, so there's many choices you can make that satisfies the condition. So it's not unique, okay? But we are also given something about the velocity. So according to the formula for velocity at time 0, my omega a and then sine times 0, so I got sine of phi 0. Okay, and we are also given that my object is moving in the negative x direction at time 0. That means v is negative at t equals to 0. So that means I want to make sure that everybody here is positive, so that I put a negative there, then my velocity is negative to be times 0. So I'm going to choose, so I will choose phi 0 as equals to pi over 2, then we'll give v0 to be negative, right? So that means my solution is x of t is equals to a and then cos omega t plus phi 0. So I chosen this to be this, so pi over 2. So if I chose this to be pi over 2, right, my position will be 0 at time 0, good. And then my velocity will be negative at time 0, right? And also I even know my amplitude. So x of t, my amplitude is 0.600, and then my omega is 5.236 t plus pi over 2. So now I can finally calculate the position at the time 0.353. So no, 0.480, right? So it's 0.6 cosine 5.236 0.480 plus pi over 2. Remember, if you are using calculator, right, your calculator, some of you might be, the calculator might be in radian, might be in degrees. Remember our calculation, we are doing it in radian. So if we do everything correctly, so I got 0.353 meters. So object is 0.353 meter away from equilibrium position. Okay, yeah, so just like that, that's how you get the answer. Okay, so that's question 1 is practicing how we get used to these types of calculations. Or then it becomes, COVID becomes the COMVID, right? F is equals to 2n pi. F? No, phi, right? You mean this one? Basically, we are solving cos phi 0 equals to 0. Right? So, yeah, so what is the solution that, what is the angle that cosine makes it 0? Right? Cosine of what angle gives you 0? So it's going to be this. Okay. Yeah, phi. Yeah. By the way, it's pronounced phi. Yeah, phi. Or phi. Actually, can also use sine function. Yeah. Yeah, phi. Yellow. So you can use sine function also. Correct. Where is it? Yes. Yeah. So this was question 1. Right. So question 2. Let us jump to question 3. It is a similar situation, but we want to calculate a more complicated situation, slightly more complicated, right? But at the end, if you know how to use the functions, also can, right? So, question 3. Phi. Or is it phi? It's the Greek letter. It's the ancient Greek. Physics. Oh, yeah. Physics also came from a Greek word, I think. Yeah, sine is actually sine is nicer because it starts from 0 and then it goes up. That in that sense, sine is also nicer. So let's go to question 3. Let's read the question first. So according to question 3, right, we have an object going through simple harmonic motion with this period and this amplitude also all given. But at time 0, right, the info given is it is this position and then instantaneously at rest. So calculate the time taken from here to here and from here to here. Okay, so let us do this question. Full screen. Okay, so the info given is the period is 0.900 seconds and then the amplitude is 0.320 meters. So the omega is supposed to be 2 pi over the period, so it's going to be about 6.981 radians per second, or just 2 pi over 0.9, or 18 over 10 pi radian. Yeah, something like that. Right, so we you can express it any way that you want, but our position, well, we shall, because I always use cosine, that is our standard formula. If you want to start with sine, also fine, it's perfectly fine. Then the velocity is obtained by differentiating the position, so I got negative omega a sine omega t plus phi 0. Okay, so let us calculate our first part. The first part is, well, let us determine our constants first. So we are given, right? So we are given the information that at time 0, my position is at 320. And also my velocity is 0 at this moment, right? So let us put in this information. So at time 0, I get 0.320 is equals to a cosine phi, right? And then at the velocity, the initial velocity is at rest, so 0 is equals to this function at time 0. So from this equation, we conclude that sine phi must be equals to 0. And then the amplitude is also the same, so 0.320 is equals to 0.320 cos phi. So cos phi 0 must be equals to 1. Sine phi must be equals to 0. So what is the correct angle that you can choose for phi? So a choice, let's call this equation 1 and equation 2. So a choice that satisfies equation 1 and 2, there's an obvious choice, right, is 0. So phi naught equals to 0. Okay, I say it's a choice because this choice is not unique. If for some reason you purposely want to choose also can, or generally speaking 2n pi, right, also is possible. Okay, so that's why it's a choice, because it's not unique, right? You choose this also, it will satisfy these two conditions. We just need to satisfy these two conditions. So why not choose the easiest one, 0? Okay, so if I choose the easiest one to be 0, then what I got is my function now is x of t is my amplitude cos omega t plus 0. So my amplitude is 0.320 cos omega t. So omega t is 6.981 radians per second, and then time. Right, so what does the graph look like? So the graph is going to look like, this is a cosine function, right? So this is a cosine function, and then the cosine function is looking like this. Okay, so this part is 0.320, so the bottom amplitude is negative 0.320, right? And then this is my time. So yeah, right, so then what we want to calculate is the time taken to reach 0.160. Okay, so right now I want to calculate the time taken for when x is equals to 0.160. So that means I want to calculate 0.320 cos 6.981 t. Okay, so can I find the t over here? Right, so if I divide this two, I just get cos 6.981 t, and then dividing this is actually the half of this, so this is 0.5, so this is like half, so that means I want 6.981 t. Cosine of something to be half is pi over 3, right? So that will give me t is equals to about 0.15 seconds. Okay, so that means what is the time taken for it to reach 0.16? So half of this is 0.16, so it's this time. So I'm going to call this t1. So t1 is equals to 0.15 seconds. Okay, so that is over here. And then the next solution is when, is there space to do it here? So when x of t is equals to 0, right? So that means it's 0.320 cos 6.981 t. So 6.981 t, how cosine of this to be equals to 0, right? So cos 6.981 t, because this one doesn't matter, if I divide down it will disappear. So how do I make this term 0? 6.981 t is, well, pi over 2. So that will give me t is equal to 0.225 seconds. So this is t2, right? So this is the time taken when it goes to 0. So t2 over here. Okay. Then finally, the last part is the time taken to go from here to here, right? So the time between x equals to 0.160 to x equals to 0 is well, how long does it take to go from here to here, right? It's just t2 minus t1. So this minus this, I will get 0.0750 seconds. Okay. What's Zhuangbility? FIZ student. Yeah, so this is physics in Malay language spelling. Right. Yeah. Yeah, so there's so last time, right, physics, math, chemistry, they are actually the same discipline, and it's only that, like, since the time of Newton, when the fields become more and more big and more complicated, then it start to separate into new branches, right? So this is kind of true throughout the any topic, right? So any topic, like you know, when one topic starts to expand more and more, it becomes too big, so it starts to become their own topic already, so they separate off into a separate topic by itself, right? So last time, right, physics, chemistry, astronomy, and astrophysics, they are all called natural philosophy. So that is the Newton's book title, right? The Principia, Principles of Natural Philosophy, something like that, right? And math also. And then, you know Hooke's law, right? The Robert Hooke, he was also a biologist because he was the person to discover the cell using the microscope, right? So everything is everything is just called science or natural philosophy last time. It's the same topic. Okay, so let's go next to question 5. Can go slower. I'm already quite slow, right? Any slower, we don't have time to finish off. Yeah, Principia Mathematica. Yeah, so actually that's the correct title. Yeah, I'll try to go slow lah, but we should finish the syllabus within time. Where am I? Yeah, here. So let me turn on again and go to the next question. So let us skip to question 5. So by the way, right, remember that we have video, so if I'm too fast, you can download the video and rewind again, and that is the benefit of having video. Well, yeah, but on the other hand, a lot of all these discoveries are actually quite long apart, right? We are having a lot of discoveries today also, and the thing about the thing about science is, like, we don't realize the importance of certain discoveries until long after. Yeah, the microscope thing, right? Yeah, and because right now there's many discoveries, and we don't realize a lot of them, and we don't follow them, is because we don't know which ones are important. So the important ones is only we realize them much later. But right now is especially when we talk about black holes and gravitational wave, right? There's a lot of amazing discovery. So we discovered those two things, gravitational waves. We took a picture of black holes. We are almost solving the Hawking paradox as well. So that is also happening right now. And yeah, and quantum gravity. So question 5, right? Question 5, we are talking about a block of mass of 5 kg sitting on a frictional surface, and then the force constant is 180. And then it's attached to this, and then there's friction. So, right, yeah, it's been a while since we done friction in chapter 2, right? But it's irrelevant here. The second block on top is 1 kg. So the coefficient of static friction is 0.4. What is the maximum amplitude such that it does not slip over the surface? Okay, so for this situation, right, let me write down the information first. My mass is 5 kg. The one on top is just 1 kg. The spring constant is 180 newtons per meter. The coefficient of static friction is 0.4. So what's happening here is, let's say this is my equilibrium point. So equilibrium point is x equals to 0. So I have a spring that is oscillating back and forth, right? So let me say that at this instant my spring is over here. So this is my big M, and then this is a little m on top. Okay, so let us consider this situation. Now the spring, right, is oscillating back and forth, and so the reason why the upper block is sticking to the lower block is because of the static friction, and as we can see, right, if you remember last time, if the bottom blocks is, if the system is accelerating too fast, if the acceleration is too much, the upper spring will slide over the surface. Okay, so let us draw some free body diagrams. So free body diagram of the upper block is what? So free body diagram of the upper block is little m over here, right? And then so let's, at this instant, my full screen. So at this instant, my spring is on this side, right? So let's say is traveling back. So if it's traveling back, right, so then I have the static friction that is pointing this way. Okay, so let's say at this instant, right, so drawing the instant where blocks are moving left. Okay, so at this instant is coming here, so it's making the box accelerate to the left. So the net force acting on the upper box is the static friction, right? There's no other force, and this is equal to mass times acceleration. Okay, so this is the acceleration of the system, and then what is the magnitude of maximum acceleration, right? So when the acceleration is maximum, right, then my static friction is equal to mu s times the normal force, and for this case the normal force is equal to mg. So from here we calculate that my maximum acceleration, I just take the magnitude because I don't want to worry about negative sign anywhere, right? I just want to know the magnitude of this. The magnitude of this is mu times s times well, so when this is so m times a is equal to mu s times mg. So the acceleration itself is equal to mu s times g, right? All right. Newton's birthday, is it on Christmas? Nah, not really. Yeah, the first human cell was discovered by Robert Hooke, I think. Yeah, unfortunately, my paper has cannot be applied to space travel, and mainly because of the negative cosmological constant. Yeah. Oh, this one is from Star Trek. Okay, that's interesting. Yeah, reminding me of Doctor Who. I haven't watched Doctor Who in a very long time. So in any case, we got this system, right? So we call this equation 1. So we got this equation 1, and now, right, now I will draw another free body diagram by treating the whole thing as a one big system. Right? And then my free body diagram is going to look like this. So if I treat this as one big object, so the total mass is m plus big M, and I'm attached to the spring, and then this is a smooth surface. Okay, so the acceleration because we're talking about the accelerating together, right? So both objects have the same acceleration, which is called a, and we can actually calculate this acceleration. So what is the net force acting on this object? So the net force acting on this object, the magnitude is kx, right? The distance away from the equilibrium position. So my force is acting to the left. My net force is kx is equals to my total mass, and then times the acceleration. Okay, so and if you remember, right, when we're talking about the simple harmonic oscillator, my acceleration is dx dt. So we got the equation that d2x dt square, if I bring this down, is equals to minus k over m plus m, and then times x. So from here, right, we recognize that this is a second derivative times a constant times x. So if I compare with the simple harmonic oscillator equation, right, this is a simple harmonic oscillator equation. With omega square being equals to k over m plus m. Okay, so that means the solution is x of t is equals to some amplitude cos omega t plus initial phase. So omega is given by this, right? But what I want, right, is to calculate the maximum, well, because when the acceleration reaches this number, then the static friction will break. So I want to see when does this happen. So I got the solution already, so I can calculate the acceleration. Okay, so acceleration is just the second derivative. So it's just negative omega square a cos omega t plus phi 0. Okay, so in this case, right, I want to find my maximum acceleration. So my maximum acceleration is, I want to find when this is maximum. Okay, so it's when this is maximum, and as we can see, right, this will be max if the cosine function is equals to 1. So I got a second equation that is given by this. So my second equation is my maximum acceleration is just omega square a. And what was my omega square? My omega square came from this. So if I put this in, right, so I got ka over m plus m. Okay, so my amplitude will determine my maximum acceleration, but my maximum acceleration is also coming from the condition where this must not be exceeded. So I compare the two equations. Okay, so compare equation 1 and 2. Well, this equation for A max is another equation for A max. So Ka over m plus big M is equals to mu s times g, right? So finally we got the solution where A itself, no space. Let's go to the next page. Okay, so we got A finally is equals to mu sg m plus big M divided by k, right? So we can actually put in the numbers now. So my maximum amplitude is 0.4, 9.80, and then 5 kg plus 1 kg. The spring constant is 180, so it is 0.131 meters or 13.1 centimeter. What? This is from... Okay, while it loads, I will just leave the paper here. Okay, so any questions so far? Tiny Hawking. Okay, if not, let us go to the next question. Yeah, so this two, the moments of inertia one is probably something less familiar, so let us do this question. Right, so let's do question 8. according to question 8, I have 1.8 kg rod from a car engine pivoted as shown like this, right? And then the center of gravity, another word I was saying is the center of mass. So center of mass is located at this point, so 0.2 cm from the pivot, and then is set into oscillation. So you make this thing oscillate, and then this information will tell us the period, and based on all this, we want to calculate the moments of inertia of the system. So how do we solve this? Okay, so yeah, I think we do have some time. This time I can go a bit slower for this question. Okay, so I have a pivot here, and then I have this object, right? It's very hard to draw, so roughly looking like this. And then according to the question, my center of mass is over here, so the distance from the pivot is here, right? So this thing is hanging there and then it's vibrating, so I want to calculate the moment of inertia based on this information. We know the frequency if we calculate from the information. So the D is 0.20 meters. And how do we get the period? So according to the information given, right, if it swings 100 times, the time taken for it to swing 100 times is 120 seconds. So one swing takes how long? So one swing will take 120 over 100. So according to this, the period is 1.2 seconds. Okay, so now that I know the period, I also know the angular frequency. So it's 2 pi over the period. So 2 pi over 1.2 is 5.236 radians per second. Okay, so I got the omega now. Then how to calculate the moment of inertia? Okay, so how do we based on all this information, how do you calculate moment of inertia? We're going to use the formula where my moment of inertia is mg times the distance over the I. Okay, hang on, this is omega, right? So I can actually solve this for I. So if I square this, right, so mgd over I, so my I is just mgd over omega squared. Okay, so this is a simple way to get the moments of inertia. So the mass, what's the mass? By the way, am I recording? Yes. Yes. Okay, so the mass is, yeah, what was the mass? I was supposed to find the mass. The mass is 1.8 kg. So we put in 1.8 kg. Acceleration due to gravity is 9.8. The D is 0.2. And omega square is 5.236 square, which we calculated above. So once we calculated everything, we got 0.129 kg meter square. Okay, so this is so the physical pendulum, right, although it looks challenging at first, at the end of the day, right, always remember the key point is to these are the two important quantities. Okay, so right now we are given this and calculate I, but most of the time for the next question we are about to do is determine I, determine D correctly, and then get the frequency. So the important point is to determine these things correctly. Okay. A black car. Oh really? Yeah, Bruce. I mean, Bruce Wayne has 2 cars. So my car is not black, that means I'm not successful. And black car is very hot in Malaysia, absorbing heat. Okay. Okay, so we are just within time to discuss the last question. Okay, so yeah, let's do this and then I will upload the solution for the rest later. For this one, right, we have 2 identical thin rods, okay, mass m and then length l, so both of them having mass m and length l. They are joined at right angles to form this object and then balance at this. So this one we can treat as a pivot, right? And if I disturb this a little bit, this whole thing will start to vibrate back and forth, and I want to find the frequency of oscillation for this case. So how do we solve this? Let us figure this out now. Okay, so the picture is I have one uniform rod and another uniform rod that is 90 degrees, right? So the length of both is L, the mass of both is M, and then this is the pivot, right? So it's hanging on something, right? Doesn't matter what it is. So if I touch this a little bit, it will start to go back and forth. So remember, right, for the moment of inertia of one uniform rod, and it is pivoted at the end, what is the moment of inertia? Moment of inertia of rod is 1/3, right? So yeah, I think people should remember by now, right? Even if you don't sit down to memorize, after you do this a few times, it's 1/3, right? It's always a rod. Every time you do rod is 1/3. Only when it's through the center is 1/12. Okay, but this is for one rod. Right now I have two rods, so the system I is equals to two rods. The total system, right? So the total system is having two rods, so it's just 2/3. Okay, so it's 2/3 ml square. And then so I got this already, and remember, right, my formula was omega is mgd over I. Okay, so I have gotten my I already, so my I is this. I want to find the frequency, so I need omega. Then how to get the distance d? So remember, right, the distance d is the distance of the center of mass from the pivot. So what's the center of mass from the pivot? I need to know what is the center of mass. Okay, so the center of mass, so let me draw it a bit bigger to make it clearer. Right, so this is a rod. Okay, so for one rod, right, if it's a uniform rod, then the uniform rod, the center of mass is at the center for this rod. For this rod is also at the center. Okay, so I have 2 points. What is the total center of mass of the system? Right, the total center of mass system is, well, by symmetry it should be this, right? So this is the total center of mass of this system. I just need to know what is the height, right? So this is the YCM. Do you agree that the rod is symmetrical, right? So the total center of mass is some point right at the center on this center line. Do you agree? Okay. Let me let you guys digest this first. Yes, yes. The question say these two rods are attached always perpendicular to each other. Yes. So it's fixed. It's always perpendicular to each other. Yeah, fixed. Okay, so everyone agree with the center of mass? At least the is right at the middle, but I don't know what is the height yet. So, but the height, right, for the center of mass is the following. Okay, so the height is, well, we can calculate the height to be, this length is L/2. If it's attached as 90 degrees, this part is 45 degrees, so it's pi/4. So the vertical height of YCM is L/2 cos pi/4. Right? So L/2 cos pi/4 is L/2√2. Okay? Yes, use trigonometry to assume. Yes. Yeah, so everyone agree, huh? Yeah, or you can use trigonometry to assume, that's correct. And then, yeah, so XCM is on the center line. Okay, but anyway, right, we have concluded, what we want is this distance, right? Because this is the center of mass, this is the pivot. Okay, so the distance is the distance between from pivot to center of mass. So what we have calculated was L/2√2. Okay. Cm is on L half. Yes, uniform rod. Correct. Yes. Yeah, so we know it's L half because it is a uniform rod. Yeah. Yeah, uniform rod is right at the center. Yeah, so in fact, right, this one is not uniform, so it should not be on the center. Yeah. But we got the D already, right? And we can finally calculate the omega. So our omega is mgd over I square root, right? So the m is the mass of the system. So this one also must be careful. I got two masses, m and m. So the total mass is 2m, right? And then times g, and then the distance d is L over 2 root 2. And then divided by I. So I is 2 rods. So 2 rods is 2 over 3 m L square. Okay, and then square root everybody over here. So actually 2m and 2m cancels each other. The 3, I can bring this up. So 3 GL, and then the 2 root 2 goes downstairs. And then I got L square. Right? So L square cancel with one of the L square. So omega is finally 3g over 2 square root 2 times L. And omega is 2 pi f. So what we want is the frequency. So the frequency is 1 over 2 pi 3g over 2 root 2 L. So that is our frequency. Okay. Any question? Okay. 454 already. Not always perpendicular can, but it's going to be harder lah. So if the rod is not perpendicular, right, then this angle is not 90 degrees. Then if this angle is not 90 degrees, there is some new angle. So you calculate. So this part will be different. Right. So this part will be different. Yeah. Then you just adjust the calculation accordingly. Okay. Any other question? Oh, if the angle always change, then let's see. If we assume no external force, the center of mass, I think too complicated. It's going to be messy. You can, I think you can do this, but probably better to use Lagrangian to solve it. Yeah, you need to write the Lagrangian of the system and then use the Euler-Lagrange equation. So using this method, not so good. Yeah. Yeah. So Lagrangian it might be possible, but we have to use Lagrangians. I guess so. Unless, because right now I can't think of an easier way lah. If this changes, right? So if this changes, then the center of mass height will also change. And we have calculated assuming rigid body. So, okay, that's another reason. Our formula is for rigid body. So if the angle changes, right? If the angle changes, then it's no longer a rigid body. That's why. It's a sum of two rigid bodies. Then, which is why we must use a Lagrangian to solve. You know? Yeah, so in any case, if there's no question, I shall stop the recording. But you can ask and I can answer later. I'll just stop the video first.